Greetings. I'm Yvonne Stapp for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. Today, we learn about the relationship between Earth's climate and the deep ocean currents. This is very important at this time because the oceans are the largest heat sink, and there are many questions, many issues. Our guest is Dr. Amy Bauer. She is the senior scientist and the chair of the Department of Physical Oceanography at the Woods Hole Oceanographic Institution. Dr. Bauer is an expert on deep circulation, the currents and eddies that move the heat and salt and minerals and marine life all over the oceans at huge distances. She will explain how these currents work, why they are so important, and how climate changes affect the currents and vice versa. And then the one in particular, the Atlantic Meridional, wait a minute, so sorry, what's called the AMOC, the Atlantic Meridional Overturning Circulation Current, a major current. And then she will describe how models work, how they gather information on the one hand, and then how they model these changes to try to predict what is going to happen with these currents. And so, Dr. Bauer, welcome, and thank you very much for joining us.
Oh, it's a pleasure to be here.
Okay, I will ask you to start with what these currents are, what causes them, and then we'll go into like how extensive they are and so on, some dynamics. So what causes these things in the first place?
The Atlantic Meridional Overturning Circulation, or the AMOC, as we call it, is actually not one current. It's a system, a very complex system of currents that extend throughout the Atlantic Ocean, the North Atlantic and the South Atlantic, from the surface to near the seafloor. And this AMOC is actually connected to the other major ocean basins in the world ocean, that they are the Indian Ocean and the Pacific Ocean. And this system of currents is a major component of Earth's climate system. And this overturning or meridional overturning circulation is critical for maintaining the climate as we have known it for millennia. And in this first graphic, I will show you what causes these currents to flow. This first graphic shows how the Earth's radiation budget works in its most basic form. Because the Earth is a sphere, the sun's rays approach the Earth more or less as parallel lines, and yet the amount of radiation per square area is much larger near the equator than near the poles. This is because the curvature of the Earth. You can kind of get that impression from these from this graphic. So it turns out then that the radiation from the sun, or the heat from the sun, is greater at the tropics than at the poles. Now the Earth is also, as well as receiving heat from the sun, it also radiates heat back in a different frequency, but it radiates energy back out into space. But that distribution is different. It's a little bit more similar from equator to pole. So the balance between those two curves, the difference in those two curves, the red one and the blue one, is actually shows the amount of heat that's actually accumulated at the equator, because there's more energy coming in than going out at the equator. So the equator heats up. At the poles, it's the opposite. There's more energy radiating back out into space than coming in from the sun. So without the ocean and atmospheric circulation, the equator would continue to heat up because there's more energy coming in than going out. It would get hotter and hotter and hotter, and the poles would get colder and colder and colder. Well, we're not in that kind of unstable situation. We have a little bit of more stability than that. And, but the reason we can keep a stable climate then is because the winds and the ocean currents redistribute this imbalance in heat. So they take heat from the equator and move it towards the poles. So that overturning, and it's called an overturning circulation because the warm water moves northward. It's light, it's hot, it's warm, it's less dense, it's at the surface. It tends to go towards, especially the North Pole in the Atlantic Ocean. And as it does, it releases heat to the atmosphere there. It gets colder and denser and sinks down and then comes back towards the equator at underneath in the deep ocean. Right. So the global effect of this, do you want me to go on to the next slide?
Yeah, if you would, do you have an illustration of that overturning of how, because we don't have a very good sense of there's warm on top and then it goes under and so on. If you do have that illustration, that would help. Thanks.
Yeah, I think we can go to the next slide.
Yeah, that's the one. Yeah.
Yeah, sure. Right. So yes, so this shows how in its very simplest form, how this works. So you see the red arrows, say, take the Atlantic, the North Atlantic, for example, between the US and Europe. You see these warmish arrows near the surface, and then you see the arrow point downward and then return back southward down deep underneath the warm water, because now it's cold and dense and it sinks down to the bottom of the ocean.
Okay, so this keeps the climate stable, and that's a wonderful illustration because it shows how global this is. And you have pointed out that there are many contributions to this, that there are many currents involved, actually.
Yes.
I suppose.
Yes.
Okay.
Yes. This is its simplest form, and it's a very valuable icon. Because it shows it in a way that's easy to grasp. But in fact, the currents are much more complex than illustrated in that graphic.
Right. Okay, we understand that now, I think. But then, so this keeps the climate stable. Now, we have a couple of things that have changed radically. One of them is atmospheric heat. So it's not just sun, but this the heat from the CO2 that is being trapped in our atmosphere, and also issues of things like fresh water melting in, which we need to understand. So what causes the changes in these currents that would destabilize ultimately?
Right, that's a great question. So you're right, absolutely right. The atmosphere and the oceans are heating up due to humankind's increase in CO2 and other greenhouse gases in the atmosphere. And that's acting just like it's called, a greenhouse. So it traps the heat under the atmosphere. Most of that heat is actually being absorbed by the ocean. So this whole overturning circulation depends on the difference in temperature between the ocean and the atmosphere. The ocean has to be able to release the heat to the atmosphere as those currents move northward, and get more dense so it can sink and come back the other way. But if the atmosphere and the ocean are too warm, then that water cannot sink.
Got it.
So that could indicate that as the climate warms, that overturning, that sinking, which is so critical to the whole system, could slow down. And it's not just the heat. There's another component to ocean water density, which is the salt content. And so the salt salt makes water denser also. So as long as the water is salty enough and it cool enough, it can sink. A change in either of those parameters, the temperature or the salt content, could change that sinking motion. So there, as well as, one of the impacts of a global warming is the melting of, say, the Greenland ice sheet.
Yes.
And the melting of Arctic ice. Both of those are contributing more fresh water to the area where the sinking occurs. And that's not good in terms of maintaining the sinking. The more fresh water you have sitting there, the lighter the water, the harder it is for the water to sink.
Okay, so there are two large factors, at least in this, to watch. But then we'll ask you in a minute about the long range, the part of this, but what would be the impact of such weakening? You've already indicated, so things, I guess, will slow down if they can't overturn, but in terms of the climate, the impact on the climate generally, but also perhaps marine life, that because that's to move, they move with these currents. I think, anyway, you know about that. What would be the impacts of a weakening of a current like the AMOC?
Sure. So I made a list of the potential impacts. I can talk a little bit about each of these. They're not all within my area of expertise, but
right. Just in general, this is a great list. Thank you very much.
Yeah, sure. Certainly, if that AMOC system of currents, which carry warm water northward and cold, dense water southward, that has a big impact on the climate of North America and Europe, in the North Atlantic especially. If it were to slow down, it has been projected that Northern Europe, which has a relatively mild climate for its latitude, would get colder, most likely. So that's one potential impact. The path of that warm water that goes northward has a very important impact on storm tracks. So these are, for example, the nor'easters that come up the east coast of the U.S. And then they sometimes impact maritime Canada. Sometimes they go all the way across the Atlantic and influence the UK and mainland Europe. As that path of that warm water could change, and therefore those storm tracks could change. And this would have huge societal impact, because those, people might be getting more rain and more wind and storms that aren't used to it, and vice versa. The amount of warm water that is transported northward by the AMOC has also been shown to have an impact on Arctic sea ice. Some of this warm water goes all the way up to the Arctic. And if it's getting, warmer and warmer, it's going to cause more Arctic sea ice melting. That in turn adds more fresh water to the system, which I mentioned could also contribute to a slowdown. So it's sort of a positive feedback loop potentially there. There's also been shown to be relationships between the strength of this overturning circulation and sea level, especially on the east coast of the United States. A slowdown in the AMOC could accelerate sea level rise on the east coast. Even without the AMOC, there will be sea level rise. We're already experiencing it, actually, just due to the warming water, because warmer water has more volume. So it just, rises higher. So it comes higher up on the beach. But a slowdown in the AMOC could also exacerbate that problem. There have been shown to be relationships between the strength of the AMOC and sort of drought and precipitation patterns over Africa and the Sahel in particular. And then getting to your point about marine life, there's, as the patterns of where the warm and cold waters are, as that shifts, the species of plants and animals in the ocean are highly adapted to particular temperatures. So as the patterns shift, where we find certain organisms will also shift. So I call that biogeography. You know, where do you find fisheries, lucrative fisheries, say on Georges Bank or the Grand Banks of Newfoundland? Those are sensitive to ocean temperature. So those could also shift. So a fishery, say off New England, that's been very active may in fact, decline or move elsewhere.
Right. That's great information, and thanks very much for that. And now I'd like to turn to the fact that, of course, you've done lots of studies on lots of currents, and so I'm going to pick at this expertise a whole bunch now.
Okay.
I would like to know how you study this, how scientists like you actually study this, and then would like to move to how you model it and ask some
Okay.
about that.
Sure.
That is looks like the best fun to go out and study this stuff, but it's very complex.
It is. It's very difficult. The ocean, for one thing, we can study the atmosphere quite easily because we can make observations. We can use our own eyes, to see what's going on. But also, all the sensors that we use to measure the atmosphere can send all their data back to us through radio waves, basically. So it's and the atmosphere is very transparent to that, so it's very easy. You can send weather balloons up all the time, all over the place, and get the data back instantly. You can feed that data into numerical models of the atmosphere, and that's how we come up with weather forecasts. Okay, the ocean is completely different environment. You cannot send all this information by radio waves through the ocean because the ocean is completely opaque to radio waves. So we have to use all kinds of other techniques to measure the ocean in a similar way to measuring the atmosphere. This is an example of an observing system that we have in place right now that I'm participating in. It involves about 7 countries, I don't know, more than 20 principal investigators. It's such a mammoth effort that no one country or institution or principal investigator can do this on their own. This has to be collaborative. It's so expensive and it takes so many ships, so much instrumentation that we have to do it as a collaborative effort. So this is a cutaway view showing the locations of moorings. These are deep sea moorings. It's just like a mooring that you might put your sailboat on in a harbor, except that it's miles long, has a 2,000-pound anchor on the bottom.
Oh my goodness.
And all kinds of floats to keep it upright in the ocean. And then along the mooring line, we attach sensors to measure the temperature, the salinity, and the currents. And in order to really get an understanding of the AMOC and how it's changing, we have to measure all the way across the entire Atlantic, from boundary to boundary. So from Labrador, in this case, from Labrador to Greenland, and then from Greenland to Scotland, all the way across. So this involves something on the order of 60 of these moorings. We started this program in 2014, and we have funding to make these measurements for 10 years. So that's the schematic, but how do we actually get that in the water? I'll go, this is the really fun part.
Yes. Oh, wow.
This shows what I was just saying about how ocean currents, temperature, and salinity are actually measured by sensors on individual moorings. Getting these moorings in the water is, I call it industrial oceanography, or hard hat oceanography. We do this from research vessels, and there's usually a group of, say, 20 to 30 scientists and something like 20 professional crew members. And we go out for a month at a time, or sometimes less, sometimes more. And as well as putting those moorings in the water, excuse me, as well as putting those moorings in the water, we also take water samples while we're there on the ship. So we use that to calibrate the sensors to make sure that they're measuring accurately. And this shows some pictures about how we do that. lowering basically bottles over the side all the way to the sea floor. And then we close the bottles when they're down deep and pull up a water sample. And then we measure its temperature and salinity and other properties that way. That's a lot of fun too.
Yes. Ah.
Another way that we measure ocean currents, especially down deep, is by using freely drifting objects that we lower, that we release. They're not attached to the ship. We release them down, they sink down to the depth of the deepest currents, and then they drift around and they're tracked underwater by sound. Sound, it turns out, travels very well underwater. Sound travels very well underwater where light does not, but we're able to track these floats and where they go, and they can map out the pathways of these currents and how they're changing. In a very relatively new development now, we're taking advantage of technological advances in miniaturization of electronics to build robots, basically, that can go out and prowl the oceans, and they can dive down deep into the ocean and then come back up and kind of seesaw their way across the whole Atlantic Ocean. And they can also measure currents, temperature, and salinity as they do so. They go very slowly. They only go about, maybe a half a mile an hour. Okay. Yeah, they go very, very slowly, but you know, they do it on their own. They're autonomous, and so they're proving to be quite cost effective in some situations.
Right. I imagine it's very accurate also. It's a very good way of getting accurate information. It's great.
Yeah, yep. So those are some of the ways that we're actually trying to measure the ocean from top to bottom and from coast to coast.
Great. That's so wonderful that you can illustrate how this is done. There are two things there that, first of all, this is complicated equipment. You've got to get out on ships and so on. The other is it's a cast of hundreds.
Yes, yes.
And so you have a lot of experts. And another thing that you indicated is that this is an international effort. This is science is by default international anymore. You know,
Yes.
It's big studies. And one more thing that you brought up is that it takes time. So you have a 10-year study here. It's not something you can go out and take snapshots of and get an answer right away. So thank you for sort of underscoring that complexity. Now, when you get all that data,
right.
Tell us what you do, because you're pretty famous for modeling and so on.
Well, we do many things with this data. Sometimes, for one thing, we look at this data just on its own. And what we can do with all that mooring data in particular is we can construct a time series, we call it. So that's just I'm trying to think of another word to use for time, a time series, which is just the changes in the AMOC. We can measure the AMOC strength. Uh-oh, can you still hear me?
Oh, yes.
Okay, I got an internet unstable message, so.
Oh, yeah, right. It's Monday.
Yes, right. So with these data, we can actually measure the AMOC every day. And then we can put it all together and, you know, over right now, so far we have 6 years of data, and we can then see how the AMOC changes day to day, season to season, and year to year. And we have identified some variations in the AMOC that we did not anticipate. Already we have new results showing that the AMOC changes quite a bit from month to month. All right. And we are just now trying to dig in deeper and understand why that is. We don't know yet. It probably has something to do with changes in wind patterns.
I see.
Yep, because the wind, I didn't mention that at the beginning, but the wind also has an impact on the AMOC. as well as the heating and cooling in the freshwater.
Right, right,
Yeah.
right.
Yeah, the winds do too. So we're trying to put it together and be able to explain these month-to-month variations. What we haven't seen yet in 4 to 6 years is any sign of a substantial weakening of the AMOC from the data alone. It's the tricky part about the AMOC and trying to look for long-term trends is that those long-term trends are expected to be not large so far, not enormous, but these fluctuations from month to month are enormous. So think of it, you have a very noisy signal with big fluctuations,
Yes.
month to month or year to year,
Right,
or even decade to decade. And so in order to observe a very slow trend that
yes,
may or may not be occurring, you have to measure for a long time.
right.
So you can filter out that month to month variation.
Yes.
Yeah,
That's
so
really, that's really great information. Yes.
yeah, we really, and we need to, this is something new for oceanography.
Yeah.
Typically we've been observing oceanography, typically we've been observing the oceans, and doing projects on sort of one scientist's lifetime.
Yeah.
Okay. But what we need now is to make commitment to long-term ocean observing.
Yes.
Decade after decade, spanning multiple careers of the ocean scientist.
Yes, right.
So that's something we're working very hard now to put in place.
I see. So this is very important also, that you've got to look at a very long term of data. Right? And so then I suppose you go and build models on this, like to try to predict it. You have to do the models. And is that very complicated with data like this?
Yes. The models themselves are very complicated. So I'll try to explain what a numerical model is. It's basically there are equations, we call them the equations of motion, which these are mathematical equations that describe the balance of forces that act on ocean currents.
I see.
Their origin is in Newton's laws, okay? F equals ma, right? Force equals mass times acceleration. So some of you probably learned that in high school physics class. And the equations of motion that we use to develop these models are really nothing more than extra elaborations of F equals ma. Okay, so we put together these sets of equations, and then we usually use computers to help solve those equations to be able to predict currents and how they'll change in the future. All right.
Right.
So, but we don't always have all the exact terms correct in the equations because we don't know yet how to represent, say, friction in the ocean. Sorry, I'll put that on mute. Yeah, we don't necessarily know how to represent all the forces that we know are important, but they're hard to represent with mathematics. Friction is sometimes one of them. And there are others as well.
What do you mean by friction in terms of the ocean, please?
Right, sure. Yes, they're ocean currents. When they're flowing through the ocean, they're almost, think of them as like a river, sometimes through the rest of the ocean, which may be not moving as fast. So it's almost like a river flowing in a riverbed, right? And the river is rubbing up against the sides of the riverbed, right? And on the bottom as well. And that causes friction. If there's not another force that will keep the water moving, the friction will eventually slow it down.
Okay.
So just like a sled on snow, right? When you're sliding down a hill, you have gravity pulling you down the hill, but you actually have friction trying to slow you down. And as you get to the bottom of the hill, the gravity starts to be less because you're not on the slope anymore, right? You get onto the flat part, and eventually you come to a stop because of friction.
Right.
Okay. So the same force acts on ocean currents as well.
Okay.
There's friction with other water and friction with the bottom of the ocean and with the sides of the ocean basins as well.
Right.
Yeah.
Okay, so it sounds, thank you for that clarification, but that sounds like this is like an ongoing process of developing these models, making the corrections, bringing in the data, and a lot of head scratching because it's very complex information or very complex data or dynamic system like this.
Yes.
So what can you tell us, and also that it needs to be long range, that
Yep.
have to cover a lot of time. And
Right.
So you've done a great deal of this, and could we get your take on what is going to happen with, emphasize the AMOC because that's a major one, and there's been a lot of media attention to that, but
Sure.
it's uneven. And so what is the view from science and in your perspective, especially a long range study like this, that in terms of what's going to happen in terms of the weakening or not of this?
Right. Yeah. I'll answer that question. First, I just want to address another way in which we use the data. And we use the data also to test the models. Right, to see how well we're doing with the mathematical models. That is critical. That helps us improve the models. If we compare them to the real observations, which is what the ocean is really doing, and then we test that. Does the model reproduce the same thing? So that's how we improve the models. Okay?
Got it.
But the models aren't perfect yet by any means.
Right.
But we have a lot of people doing this kind of modeling development and using very different kinds of models, which is great because, you know, we can't be sure that any one model has it absolutely right. We need to try many different approaches, right? And so what the models are saying at the moment is that the AMOC will likely gradually slow down over the next 100 years.
Okay.
So that most likely due to warming, not so much yet, you know, in the next 100 years to the freshwater component. But it will, just because of the warming, that sinking motion will be inhibited, and that will cause a slowdown in the AMOC.
Okay, but what you are not seeing is something rapid. It's
correct.
Not happen in the next 2 weeks or the next 50 years. It's a slow process, and that's quite assured from what you are observing and your very careful analysis of this.
Yes.
That's an extremely important point. There are two things there: that the models are constantly adjusted as you get data, and that it takes big data over a long stretch of time, and that your conclusion at this time is that you're not going to have an immediate slowdown, but despite the increase in heat in the atmosphere and the increase in freshwater melt. So that's an important thing to know. Is there a consensus among oceanographic physicists like yourself on that score?
Yes, I would say so. The magnitude of the slowdown is probably not agreed upon.
I see, right.
Yeah, but that there'll be some decline. It could be a very minor decline. It could be a little bit more substantial.
Yes.
One word many people use, especially, you know, in the maybe popular media, is collapse. A collapse of the AMOC.
Yes.
Okay.
Yes.
That is, I would say that is not anticipated by most, by the consensus. Definitely not. You know, there was a movie maybe 10 years ago called, I think it was called The Day After Tomorrow. It was a fictional Hollywood movie about a collapse and what would happen to the climate of New York City and other places, right? And they show sort of a deep freeze almost overnight. You know?
Yes.
Pure science fiction.
Okay, good. Bring that point out, but for sure. But there are also, even in good sources, there's some variation. But what you we're not sure, well, because lots of people are doing scientific experiments, but we want to make sure that people understand that there's still some uncertainty here, that
Mhm.
are committed to very long range, very careful analyses of what they're observing, and that the technology is improving very quickly. Actually, like these robotic things are
Exactly. Yes, and the models are improving as well, and our
Yes,
computational abilities are also improving. So these
yes,
models can be more complex and run faster.
yes,
So, and that's also a very important advancement over
yeah,
the last couple of
see.
decades. Yeah.
I see. That's very, very interesting. And Dr. Bauer, before we leave you, then can we, about these other currents, we've sort of emphasized the AMOC because that's the one that gets a lot of attention right now. But should we be paying attention to some of these other big currents as well?
Yes, there's one set of currents in the tropical Pacific Ocean that has been shown to have a major impact on climate as well. It's
Ah,
called the El Nino.
oh,
Um,
yes,
you've probably heard of it. El Nino,
yes.
it actually in physical oceanography, we refer to it as ENSO, which stands ENSO, right, which stands for El Nino Southern Oscillation.
I
The
see.
El Nino piece is the ocean changes, and the southern oscillation is the atmospheric changes, but they're all
Ah,
part of a coupled system. They work in tandem, and those that system, there are El Nino events that happen at a somewhat irregular time, and trying to figure out how to predict them is challenging, but we're making progress on that. And they very much affect the temperatures, the sea surface temperatures in the tropical Pacific. And that, it turns out, has global implications. The Pacific is a huge ocean
yeah.
basin. And so that tropical region covers a huge part of the global surface area. So
Mhm.
those temperatures there have important impacts on storm growth, um, storm tracks, and climate signals that propagate around the globe. So that's another one to pay attention to.
Okay, thank you for that. I think we're a bit more educated now, but there is a real need to get this kind of information out to the public, and it's hard to understand. If you don't have the background, it's very complex and so on. But I think in the public, we need to commit ourselves to learning more about it as well. But I hope that you get out there a whole lot because you're so informative, and you've done such a range of these projects. So on our website, and perhaps we'll insert it in the introduction for this video, we'll direct people to your website where they can see these different projects that you're engaged in. And so,
Sure.
and I'd like to point out that Woods Hole is just great about communicating with the general public. That outreach is much appreciated.
Oh, thank you. Yes.
Bauer, thank you so much for joining us today. It was really interesting to hear all of this. And it's a relief to know that the ocean isn't going to collapse tomorrow.
Yes, I agree. I agree. Well, it was a pleasure talking with you, Yvonne.
Oh, thank you very much. Bye now.
Bye-bye.